Bam! Mr. Tarrou, in this Algebra 1 lesson, we are going to extend our understanding of inequalities. We just went through solving one-step inequalities, first with addition and subtraction, then multiplication and division. We took a look at a lesson solving multi-step inequalities, and finally, we're going to look at compound inequalities. Now, that means that, or in this lesson, we are going to first define what a compound inequality is. We're going to be graphing some compound inequalities on number lines. We're going to then turn it around and look at a number line graph, and from it try and come up with the inequalities represented by that drawing. We are then going to work through two algebraic examples and finish with our favorite, everyone's favorite, word problems. Okay, so a compound inequality. Well, if an inequality is a math sentence that uses an inequality symbol to compare the value of two expressions, then a compound inequality is a combination of two unique inequalities joined by the word and, or. Now, with a compound inequality, if you have these two unique inequalities but they're joined by the word and, a solution to an and compound inequality must satisfy both inequalities. And so we're going to start off by, looking at a compound inequality joined by the word and then see what that looks like on a number line. And how we need to be aware of the fact that the solution needs to satisfy both of those conditions or be a solution to both of those unique inequalities. A solution to an or compound inequality may satisfy both of those inequalities, or it can just be a solution to one of them. Opens the door up for more possible solutions with the idea of or. So we have x is less than or equal to 7. Now this has already started. This is not a compound inequality. It's just, give me on a number line graph, represent any value which is smaller than, less than 7, or equal to. Well, because there's an equal sign, we're going to put a solid dot, and the numbers get smaller as we go to the left. So here we have the graph representing x is less than or equal to 7. Here we have x is greater than -1. So we're going to put an open dot on -1, open dot, because there is no equal sign. The open part of the inequality is towards the x, so x is representing all of the values which are bigger than -1, larger than -1. Greater than -1. And that happens, or you'll find those values when you go to the right on the number line. Well, here we've got three examples. They all say the same thing. I want to basically graph a solution to, make a number line graph that represents the solutions to a compound inequality joined by the word and. So here's one unique inequality. X is greater than or -1, almost said equal to, and x is less than or equal to 7. Well, I can write the word and. I can use this set notation, sort of like a U-shape opening down, like you can see here. I don't know why I'm doing it with my hand. So both of these, word and, that means and then also I can, since with compound inequalities, the solution needs to be, a solution to both of the inequalities, you can write it as one sentence and go, okay, what are the values of x that are going to be larger than -1? Notice I turn this around. The open side of the inequality is towards the x, and it still is towards the x. So x is greater than -1, and it's sort of in between, less than or equal to 7. Okay, so if I bring these graphs down, we had something sort of special happening at, -1. So I'm going to bring that down to these graphs. And we had something happening at x equals 7. These are sort of like the critical values, if you will. Well, you can see, like, say with this purple inequality, for a while, the values of like 0, 1, 2, 3, and there's all kinds of numbers in between, like decimal versions as well, and fractions and irrational numbers. There's, this is a solid line, so all these values of 0, 0.5, 1.1, pi, which is approximately 3.14, this purple line is sort of overlapping the same area or the same part of the number line shaded by the inequality x is less than or equal to 7. But when you get past this dotted line at x equals 7, now we're getting to an area where like 8 or 9 these values of 8 and 9 are bigger than -1, so they are a solution to this inequality. But if I want to combine with the word and, x is greater than -1 and less than or equal to 7, well, these values of 8 and 9 and 9.5 and 10 and whatever, they're solutions to one inequality but not the other because they're bigger than 7. So if I want to graph an inequality, a solution to this compound inequality with the word and, let's see here. We have an open dot going to the right for x is greater than -1, a closed dot, and shaded to the left for x is less than or equal to 7, because you're normally, when you do these graphs, you're not going to make a separate line graph for each part or each unique inequality. And then because the and has to be a solution to both, you're really only concerned with the overlap of those two shadings. Or, to make it even neater, since I did make these two number line graphs separate, I can just take this out and this part out, because the solutions aren't, going to the left from 7 forever and going to the right from -1 forever. With this word and, or the math symbol and, or just this inequality written all together with this one sentence that has two inequalities in it. I was going to call it an eraser. I don't know what you call that. My rag is down. But at any rate, my eraser down. You want to shade just the area between those critical values. So this is now how the graph of a compound inequality is going to look on a number line generally, with the idea of this and idea, combining the two inequalities, making one compound inequality. Now if I put this math symbol in, if I take this U and I turn it upside down and I have it opening up, well, that represents the word or. Okay, well, now going back to that graph that I've erased, let me make a new one. -1, open dot going to the right, and solid dot on the 7 going to the left. So not graphing the compound inequality, I'm making two separate graphs that represent each unique inequality. Well, a compound inequality joined by the word or, a solution can satisfy both inequalities, but it can just satisfy one of them. So what part of this number line shows a solution or is a solution to at least one of these inequalities? Well, looking at the arrows and going in both directions for forever, -2 is a solution to x is less than or equal to 7. 2 is a solution, you can see here with the overlap, to both of these inequalities. And 8 or 9 or 10, those are a solution to x is greater than or greater than -1. So actually the shading that would satisfy this compound inequality with the idea of or on it, the entire number line is a solution. Every single real value is a solution to that compound inequality. Now, maybe a little bit of a better idea with this compound inequality with the word or. Let me break up my fancy picture. We have x is less than 2/3, or the U symbol opening up, x is greater than or equal to 17/3. Well, let's see here. 2/3, that's greater than 0 and less than 1. So we're going to go to a little bit closer to 1. We're going to put an open dot because there is no equal sign. And we're going to shade to the left because, well, it says x is less than 2/3, less than or smaller than 2/3. Those numbers are to the left. And for x is greater than or equal to 17/3. Well, maybe I'm not quite sure where 17/3 is on the number line, so we're going to do 17 divided by 3. How many 3's will go into 17? 3 times 3 is 9, 3 times 4 is 12, 3 times 5 is 15. Now that's going to give us a remainder of 2, so 17/3 as a mixed fraction is going to be 5 and 2/3. Okay, so we have that sort of same 2/3 idea. 2/3 is going to be more than a half, so it's going to be closer to 6 than it's going to be to 5. So here is 4, 5, and 6. We're going to put a solid dot this time because of that equal sign. And we are going to shade, this is x is greater than. So the numbers get greater than or larger as you go to the right on the number line. And that is the solution or the drawing, the number line drawing graph for this inequality. Now, get some of the glare out of here. And I temporarily replace it with and. I would have to erase all the shading because there's no overlap in this graph. So there would be no solution to this inequality with the word and. But that's why I wrote it with the idea or the symbol representing or. And that is how you define or the definition of compound inequalities and how you graph them on a number line. Now let's do the reverse. Let's look at a number line and come up with some inequalities and do an algebraic example. Bang! So we have our three number lines. Our first one is got a solid dot on -4, an open dot on +3, and you can see that it is shaded in between these values. So that's probably going to be an AND statement. So we're going to have, let's see here, this, what have I shaded? I've shaded everything that is equal to -4 or to the right up until, so it's not just x is, well, I'll just write that. We could say x is greater than or equal to -4, but it doesn't start at -4 and go to the right forever, does it? No, it stops at 3. So it has to be, these values need to be greater than or equal to -4, and these values need to be less than, well, let's try that with the x first. X is less than 3. Well, that's one way of writing our answer. Another way of writing this answer is we could use that set notation and say that x needs to be greater than or equal to -4 and x needs to be less than 3. With these compound inequalities joined by the word and, you can write one single sentence with two inequalities in the same sentence. So we can say that x, let's turn this around, the open side of this inequality is towards the x, so we're going to turn that around as well and leave it with that same orientation, open towards the x, and have -4, and then 3. So -4 is less than, -4 is to the left of all of this area that is shaded, at least up until you get to 3. And so when you're to the left, or as you move to the right on the number line, let's say that, those numbers get bigger. So -4 is less than or equal to x, which is less than 3. Now, you might also be looking at these type of graphs and not be using inequality notation, but interval notation. So another way of writing this statement with interval notation is to say, okay, well, the shading is starting at -4 and it's including that value. So we're going to use a square bracket and put the sort of minimum number, the smallest number first, which is going to be our -4, comma, go up to the largest value, which is included in the shading on the number line, which is +3. And how we write this with interval notation is to recognize that this inequality does not have an equal sign as part of it. It's just x is less than 3. Like you can go all the way up to 2.9, and you show that with a set of parentheses. So now, these grouping symbols don't really have a difference in meaning when you're just using them as grouping symbols, like parentheses, nested parentheses, or brackets, when you're doing like order of operation type stuff. But when you're looking at inequalities, the square bracket includes that value. It basically implies an equal sign, and the round parentheses does not. And when you use this interval notation, it is small number first, and then large one. Now, here, we don't have any overlap in our number line. So the solution, there would be impossible to write some kind of and compound inequality because there's no overlap to this graph, this number line graph, and therefore there'd be no solution. So it must be an or statement. And to write some inequalities for this one, we're going to say, I don't know, how about x, that's an open dot, so x is less than 2. Excuse me, -2, or, because that idea of or again, we only need to satisfy one of the inequalities. It's okay if we satisfy both, but we can, generally just satisfy one of them. We're going to start at positive 5. It's a solid dot, so x is going to be equal to, and we're going to the right. This area is to the right of 5, so all these values are larger than 5. X is greater than or equal to 5. Now, we can write that a few ways as well. We can say that x is going to be less than negative 2, or x is greater than or equal to 5. We can also write this inequality with this interval notation as well. Look at the shading on this number line. It's going to go like to the left forever. So if you're basically going down to or to the left all the way to negative infinity, you're never going to stop. So we're coming up from negative infinity up until negative 2. Now, negative infinity and positive infinity, those are sort of theoretical ideas. There's not like one smallest ever number, negative infinity, and there's not one largest number, like, you know, a million's not the biggest number. You can just say 1,000,001, right? And then there's 1,000,002, and so on. So infinity is sort of like a mathematical idea. And because of that, when you do interval notation, the infinity symbol always has parentheses around it. So we're coming up from negative infinity up until 2, but not exactly negative 2. I keep forgetting the negative sign. Not exactly negative 2, but just to the left of it, just a little bit less. So from negative infinity up to negative 2, round parentheses, not including the negative 2 as part of our solution, or, okay, we do have a solid dot on the 5 though, so that is part of the solution. And then from there we shade to the right or extend to the right to positive infinity and beyond. Voila! That is a few ways of writing some solutions to that number line. Now for our third inequality, this one is probably, maybe this would be a better example if I'd started with the inequality and came up with a number line. But going from a number line to inequalities, there's really kind of two answers here. Are you going to write an answer that represents the overlap area where we have, you know, values which are a solution or satisfying both inequalities? Now let's see here. We do have an open dot on negative 1, so and it's going to the right. So we have x is greater than negative 1. We have x is greater than or equal to 4. And if I want to write an inequality that's highlighting just the overlap area, that the only real solution is from 4 on, well then we're talking about, you know, values that are satisfying both of these inequalities. And you can write that as and. X is greater than negative 1, and it has to be greater than or equal to 4. Well, and means, again, we have to be satisfying both inequalities, both conditions, and this is the portion of the shading that is appropriate for that inequality. But if I want to write an inequality that says, hey, all of the shading on the number line is considered a solution, where you're not only satisfying the x is greater than 4 and x is greater than, greater than or equal to 4 and greater than negative 1, but these values of 3, 2, 1, 0, you know, 0.1, whatever, a little bit of negative numbers here, that, you know, we want to include these values as well that are a solution to only x is greater than negative 1, well then that's going to require the word or. So we can have x is greater than negative 1 or x is greater than or equal to positive 4. Now, so if this is the number line drawing, and again the whole thing is highlighted, your correct answer, the inequality, is going to be with the idea of or. If, however, you are just focusing on that overlapped area as being the part of the number line which is the solution, then you're talking about and. So let's get on to our first algebraic example right now. Solve the compound inequality and graph it. We have 2 is less than or equal to 3 parentheses. 2x minus 4 is less than 10. Now, one sentence, two inequalities, which means we do have two unique inequalities in that one statement. And if you like, you can break it up into two separate parts. You could recognize that we have a 2 is less than or equal to 3, whoops, excuse me, parentheses in the wrong spot. 3 parentheses 2x minus 4, and then you have another inequality here. Whoops, getting a little static. So with some fresh batteries, we're going to recognize that we have 3 parentheses 2x minus 4 is less than 10, and you can solve each of these inequalities completely separately and make them look like all the other inequalities that we have solved so far, the multi-step inequalities. And I'll show you a solution to that when we're done. But I'm going to focus on the one sentence that's got the 2 inequalities in it because really it's less work and more efficient for you if you'd prefer this method. Just recognize that each of these inequalities are going to break this sentence up into 3 parts as opposed to the normal 2 parts like we have with equations. And our variable is in the middle part of this compound inequality, so we're going to just move everything out of the center. So when solving equations, you can't solve for a variable when it's inside a parentheses, so we're always, like always, we're going to start with the distributive property. We're going to get 2 is less than or equal to 3 times 2 is 6x minus 12 is less than 10. And with those parentheses gone, now we can start adding and subtracting and then multiplying, dividing away from the variable and, maybe adding some like terms too if you have them. But inside this compound inequality, we have a minus 12 with the variable, so we're going to do the inverse math operation. We're going to add 12. And remember, when we're solving equations, I always say you can kind of basically do whatever you want to an equation as long as you do it once to each side to keep it balanced. Well, with these compound inequalities written in a single sentence, you have 3 parts, so just make sure you do your math operations once to each of these 3 parts. So we have 14 is less than or equal to 6x, which is less than 22. Now we're going to divide everything by 6, all 3 of these parts by 6 to undo that multiplication of 6. And we get x less than or equal to, now both of these numbers are even, so 14 divided by 2 is 7, and 6 divided by 2 is equal to 3. And that is less than 22 divided by 2 is 11 over 3. Now those are improper fractions. If you know where they are on the number line, great. If you don't, let's see here. How many 3's are in 7? Well, there's 3, 6, and 9. Okay, so there's only 2 of them, right? And I said 6, leaving us a remainder of 1, so it's 2 and 1/3. So a little bit past 2, we're going to put a solid dot because we have that equal sign in our inequality, excuse me. And then our other unique inequality, x is less than 11 over 3. Well, 3 times 3 is equal to 9. And another 3 is going to take us over 11. It's going to take us to 12. So 3 times 3 is 9. 9 taken away from 11 is 2. So 11 over 3 is a mixed fraction of 3 and 2/3. So we're going to get close to 3 and 2/3. We're going to get closer to 4 than we are 3 because 2 over 3 is larger than a half. Like 1 divided by 2 is 0.5 right in the middle. And 2 divided by 3 is 0.6 repeating. It's a little bit larger than 0.5. Now there's no equal sign here, so we're going to put an open dot close to 4, and we are looking for x's greater than 7 over 3, so we're moving to the right. And, this is one sentence with one variable, so we're using the word and to combine these 2 unique inequalities. X is less than 11 over 3. So, we have some shading over here to the left forever for the less than. We have some shading to the right forever for the greater than. But we are only looking for the idea of and. We're only looking for the part of this number line that is a solution to both of those inequalities. So that would be passable as an answer. Your teacher may want you to just be even more clear and focus your drawing like this. Now, we're pretty much done with this. I'm going to step off and just, basically really show the same steps I did over here, just once for each of these inequalities. Sorry about the dogs. And then we're going to do our next example. Bye! Negative 2 parentheses x minus 2 over 3 plus 4 is greater than negative 1, or 3/4 x minus 1/2 is greater than 19 over 2. So with the compound inequalities joined by the word or, you have two unique inequalities. So you're not these generally just end up looking like two separate problems, and there's no way to get around it. And I also include a lot of fraction work because, hey, why not focus on a lesson where my students struggle the most? We're going to solve this bad boy for x. We're going to do that by undoing on the left-hand side of our inequality the addition of 4. So we're going to do the inverse math operation, which is to subtract both sides by 4. That's going to give us negative 2 parentheses x minus 2 over 3 is greater than negative 5. Now, a couple options I can do here. I can pull this negative 2/3 out front and write this as x minus 2. And see that in this grouping symbol we have a coefficient which is a fraction. So we can multiply both sides by the reciprocal and actually, use one less step to solve this inequality. But I'm going to multiply both sides of this inequality by a reciprocal. So just to show a different look to the solution, we're going to kind of deal with the division, which is from the fraction bar, separately from the multiplication. So we have a division of 3. We are going to do the inverse math operation. The inverse of division is multiplication. So we're going to multiply both sides of the inequality by 3. And that multiplication and that inverse division of 3 are going to cancel out, giving us negative 2 parentheses x minus 2 is greater than negative 15. I don't know what was going on there. Now, at this point, I have a couple of options. I can divide both sides by negative 2 and not distribute it through the parentheses. And I probably would do that if this were an even number. But, just to create the least amount of fraction work possible, this is going to take, well, if you're great in fractions, you can argue maybe this is one extra step. But I'm going to take the negative 2 and distribute it through the parentheses and not create a fraction until I'm done with until I'm finished with the problem. So negative 2 times 1 is negative 2x. Negative 2 times negative 2 is positive 4. Please note I did not write that minus sign automatically. I waited to do the multiplication to see what the sign was. You're going to have fewer sign errors if you do that. Is greater than negative 15. We're going to undo this addition of 4 with subtraction and get negative 2x is greater than negative 19. And then we're going to undo this multiplication of negative 2 by dividing by negative 2. And a couple of things here. I am dividing by, let's see here, give me a nice bright orange color. I'm dividing both sides of this inequality by a negative number. So I need to, when I do that, make sure that I switch the direction of that inequality. And so we're going to have x, and because of dividing by that negative, sorry I ran out of room, I don't usually like to go off to the side, is less than negative 19 divided by negative 2 is positive 19 over 2. Now let me just check my work to make sure I didn't do something silly. Okay, so we are looking at x is less than 19 over 2. Great. Okay, so that is done. And we're going to go to 19 over 2. Well, let's see here. 19 divided by 2, that's going to be 9. 9 and 2 is 18. Gives me a remainder of 1, so that's 2. And, or excuse me, 2. That's 9 and 1/2. All right, just so I know where to put this 19 over 2 on the number line. So a nice open dot on 9 1/2. So between 8 and, between past 9 and not quite to 10, just in the middle. So open dot between 9 and 10. It is less than, and our numbers get smaller as we go to the left on the number line. So that is, half of our answer. Now coming over to this other inequality, and let's do that in yellow. Hopefully it shows up enough in the camera. Differentiate the 2 plus the line. Now we have 3/4 x minus 1/2 is greater than 19 over 2. Okay, let's see here. a lot of students that aren't good in fractions want to get rid of them before they even start the problem. And if you recognize that a fraction bar means division, you can undo that division. You can cancel out those fractions by multiplying the lowest common multiple between all of those denominators. Now, if I did that, if I said, okay, well, the lowest common multiple between 2 and 4, well, 2 times 2 is 4. I can make a 2 into a 4, and then, that is the lowest common multiple. So I can start off by multiplying the entire equation through by 4, and 4 times 3 is going to be 12, and 12 over 4 is going to be 3x. We're going to have 4 times 1 is 4, divided by 2 is going to be 2, and then greater than 4 times, let's see here, I don't know if I want to do 4 times 19 and then divide it by 2, but 4 divided by 2 is equal to 2. And then that 2 that's left over times 19, well, 2 times 20 is going to be 40, but that's 1 less twice, so it's going to be 38. And now I have an inequality with no fractions in it. And to finish that up, I'm going to add both sides by 2, and then I'm going to divide both sides by 3 and effectively get 40 over 3. But I want to show you that fraction work because so many my students aren't very good at fractions. And also, when I move this 1/2 over to the right-hand side of the inequality, I've already got a couple of, I already have some common denominators. So at least in the beginning, my fraction work is not going to be very complicated. I'm just going to do plus 1/2 plus 1/2 and get 3 over 4. X is greater than 19 plus 1 is going to be 20 over 2. Well, 20 over 2 divides out nice and even as well. That's going to be 10. So now we're looking at 3 over 4. X is greater than 10. And now when you're solving equations and inequalities, and you have a multiplication or a coefficient, which is a fraction or a ratio, you can get rid of that in one step by multiplying both sides of your equation, or in this case inequality, by the reciprocal, or in other words, flip it. Now we just simply have a 10. That doesn't look like a fraction, so let's put that over 1 so we can see the numerators and denominators line up. And we have the 4's are going to cancel, the 3's are going to cancel, or we have 12 over 12, which is equal to 1. So we have x is greater than, here you got again, we have again 40 over 3. Now, how many 3's are in 40? Looks like 13. So 1 times 3 is 3. Subtract, and we get 1. Bring down the 0. How many 3's are in 10? That's going to be 3, giving us 9, remainder of 1. So we're looking at 13 and 1/3. So we're going to put, let's see here, again, an open dot on 13 1/3. Just get a little bit past 13. And open dot maybe right there if that's 12, 13, and 14. We're looking at greater than, and that is the end of this second algebraic example. Let's get on to our last example, which is a word problem. Last example. To earn a B in a class, your test average needs to be between 80 and 89 inclusive, meaning those values at the beginning and end of the interval are included. So it's not an 81, it's not an 88, it's including the values from 80 to, all the values including 80 and 89. If your first two grades, test scores, were 72 and 81, that's not all that great. You need to watch a little bit more Prof. Rob Bob. What possible scores on a third test would earn you a B average in that class? Well, okay, let's start off with how do you find an average? What's the average of these two numbers? I would add them up and divide by 2. Well, if you have 3 tests, you're going to add those 3 test scores and divide by 3. It's just that I don't know what the third test score is. But I do know how to find an average. It's 72 plus 81 plus some unknown test grade, which is yet to be taken. And the sum of those 3 tests will be divided by 3 to find their average. Now, you want your grade we're looking at having a B average, so we're looking at being between 80 and 89 inclusive. So this average needs to be greater than or equal to 80 and less than or equal to 89. And hey, it wouldn't hurt if you went over 89 and got that A, but with a 72 and an 81, let's just make sure we have a B, right? How are we going to solve that inequality, that compound inequality? Well, it is a compound inequality. For a B average, you need to be greater than 80, greater than or equal to 80, and less than or equal to 89, just to emphasize that again. And it's also, you can also see that in our sentence, the one sentence with the two inequalities. And those two inequalities are breaking our inequality up into three parts. So again, I'm not going to write this in two separate unique inequalities and just do that much more writing. I'm going to keep it in this format. Our x is in the middle. We need to undo, we need to move away all of these math operations, these numbers that are included in the middle, that are in the middle of this compound inequality with the x. Fraction bars mean division. So the inverse math operation to division is multiplication. So we're going to grab an orange colored chalk and we're going to multiply each portion of this inequality by 3, except now I'm looking at it and it looks like an exponent of 3, but I do mean multiplication. So 3 times 8 is 24, so 3 times 80 is 240. Is less than or equal to, now let's go ahead and add these together. 70 and 80, well 7 and 8 is 15, so 70 and 80 is 150. Now we're at 152, 153 plus x is less than or equal to, well, there's two ways you can mentally work out 89 times 3. You can do 3 times 80 is 240, and keep that in your head. And then 3 times 9 is 27. Now I said 240 and 27, so that'll be, what is that? 240 and 27 is 267. But really, I think it'd be easier just to let that 89 round up to a 90 and do 3 times 90 is 270, but it wasn't 90, it was one less than 90, was 89, 3 times. So 270 minus 3 is 267. Now, in the middle here, we have the 153 plus x still. We have, that addition of 153. We want to undo that, so we're going to subtract all three parts. All three parts, I'm writing 3. We're going to subtract 153 from all three parts. I'm going to stop talking. Hold on. There we go. We're going to subtract that 153 from all three parts of our inequality. That's, of course, going to cancel out, and we're going to get x is less than or equal to, okay, so let's see here. 240 minus 100 is going to be 140. 140 minus 50, 14 minus 5 is 9, so we're looking at 90. And 90 minus 3 is 87. Okay, so if you want to earn that B average with these three test grades, the lowest you can get on that third test is an 87. Now, can we get above 89? Can we get into the 90s? I know it's not part of the question, but 267 minus 100 is 167. 167 minus 50 is going to be 117, and 117 minus 3 is going to be 114. So if we're talking about percentages, you're probably not going to earn an A in that class since you started off with such a low grade of 72. But you can get, you have a good opportunity to earn a B in that class, and maybe if you get some extra credit, you can get above that 114 and get yourself into the A's. But this is the end of my last example, the end of my lesson. I'm Mr. True. Go do your homework.